Finding local min, max, and saddle point using the second derivative test. First, we find all critical points. We could do this by taking the partial of the equation 4y e to the x minus 6e to the y with respect to x and respect to y. With respect to x, it equals 4y e to the x, and with respect to y, it equals 4e to the x minus 6e to the y. Because there's an x and y in both partials, the critical point can only occur at or when both partials are equal to 0. Therefore, we can conclude that y equals 0, and because of this, we could find x by solving for x, knowing that y equals 0. So we get the equation 0 equals 4e to the x minus 6. With this, we could factor out a 2, then divide by 2, and we get 2e to the x minus 3 equals 0. Then we could add 3 to both sides, and we get 2e to the x equals 3. Then we could divide by 2, and we get e to the x equals 3 over 2. So x equals ln of 3 over 2. Now we have the critical point. Ln of 3 over 2, comma 0. Now we could use the second derivative test to see if it is a local min, max, or saddle point. We can do this by solving for d and plugging in the second derivatives that we need. The second derivative of f with respect to x is 4y e to the x. The second derivative of f with respect to y is negative 6e to the y. The derivative of f with respect to x, y, is 4e to the x. And when we plug that into the equation that we have for d, we get negative 24y e to the x plus y minus 16e to the 2x equals d. Now we can plug in ln of 2/3, comma 0 into the equation to get d. Negative 24 times 0, e to the ln of 3 over 2 plus 0 minus 16e to the ln 2/3 times 2 equals negative 48. Since d is less than 0, we can conclude that the critical point is the saddle point.